Today, we are diving deep into one of the most extreme engineering environments you can possibly imagine, a modern semiconductor fab. You see, these places aren't just factories. Oh no, they are fortresses, and they're fighting a constant war against an enemy you can't even see, vibration. So how do they pull it off? I mean, that sounds completely nuts, right? But for the people who build and run these fabs, it's a very real threat they think about every single day. The stakes are just astronomical, and it's all because the things they're building are almost impossibly tiny. 2 nanometers. That's the scale we're talking about for the circuits being etched into silicon wafers in the latest fabs. Just to give you a little perspective here, a single human hair is about 80,000 nanometers wide. So at a 2 nanometer scale, the tiniest little tremor, a truck rumbling down the street, a nearby train, even the building's own AC kicking on, that's not a tremor. That's a catastrophic earthquake that can knock lasers out of alignment and just instantly destroy millions of dollars worth of product. So how on earth do you build a place that can stay perfectly still when the world around it never, ever stops moving? Well, you do it like you'd build a medieval fortress. You start with the outer defenses, and you work your way in, layer by layer. The first 2 big lines of defense are all about cutting the entire building off from the ground it's sitting on. First, you have to deal with the constant, everyday vibrations from things like traffic. And then, you have to plan for the absolute worst-case scenario, a huge earthquake. And this is where it gets really clever, right from the start. Before a vibration can even dream of touching the fab's foundation, it gets cut off at the pass. Engineers dig these gigantic trenches, basically moats, and they fill them with materials like EPS geofoam. This barrier acts like a mirror, reflecting and bending those energy waves from things like high-speed trains, just steering them right away from the building. And get this, it works. It works really well. These external barriers all by themselves can knock down ground vibrations by 60 to 70%. That is a massive first step, but it's not going to be enough to handle the big one. For that, you need something way more dramatic. You pretty much have to make the building float. You have to decouple the entire thing from the planet itself. So the key here is kind of the opposite of what you might think. Instead of making the building super rigid, you actually make its foundation flexible. And there are 2 amazing ways they do this. You've got lead rubber bearings. Think of them as massive shock absorbers for the building, where a soft lead core deforms and turns all that violent shaking into harmless heat. Then you have the friction pendulum system. This is wild. It's like putting the entire building on a giant, slightly curved dish. When the ground shakes like crazy, the building just gently skates on top, letting all that motion pass right underneath it. Okay, so we've pretty much isolated the fab from the chaos of the outside world. But what about all the vibrations being created inside the building? All the pumps, all the fans? For that, we gotta go deeper, into what I like to call the inner sanctum. And this is just a genius concept. It's literally a building inside of another building. The outer shell, that's where all the heavy, noisy machinery lives. I'm talking pumps, HVAC, the whole shebang. And it is completely physically separate from the inner clean room. There's an actual gap, a structural isolation break with its own set of support columns. Nothing touches. So all the vibrations from that support machinery, they just can't cross the gap to get to the super sensitive floor where the real work is happening. And here's why that gap is so absolutely critical. The amount of mechanical power and therefore vibration that's coursing through that outer shell can be 100 times higher than in a normal office building. 100 times. Without that isolation break, trying to make chips at this scale would be completely impossible. So this inner building stands on its own foundation, this incredibly thick and rigid concrete grid you see here, called a waffle slab. And it's engineered to meet a vibration target that just blows my mind. Just over 3 micrometers per second. That's a level of stillness that's almost impossible to comprehend. It's basically like they built their own slab of solid bedrock. But even after all of that, we're still not at zero. You'd think that would be enough, right? Nope. Tiny, microscopic jitters can still find their way through. So for the final layer of defense, we have to zoom all the way in to the multi-million-dollar manufacturing machines themselves. This is where it gets really, really cool. Every critical piece of equipment is sitting on its own active platform. This platform has sensors that are constantly feeling for the tiniest bit of motion. The instant, and I mean the instant, it feels a vibration, it tells these tiny actuators to push in the exact opposite direction with the exact same force. And poof, the vibration is just canceled out in real time. You know what this is? It's the exact same idea as your noise-canceling headphones, right? They listen for the noise around you, and they create an opposite sound wave to make it disappear. Fabs do the same thing, but for physical movement, creating this perfect little bubble of stillness for the most delicate steps of making a chip. Okay, so we've got the physical defenses, this incredible layered fortress of stillness. But during an earthquake, there's another weapon you need: time. The smartest fabs don't just survive an earthquake, they actually see it coming. Here's how. When a quake happens, it sends out two kinds of waves. The first one to arrive is the P wave. It's super fast, but it doesn't really do any damage. But trailing right behind it is the S wave. That's the slow, destructive one. The Fab's early warning system detects that harmless P wave, and it knows instantly that the destructive S wave is on its way. This gives the Fab a warning window. It might only be a few seconds, but for a computer, a few seconds is an eternity. And in those few precious seconds, an entire automated safety sequence just kicks into high gear. The system automatically shuts off hazardous gas lines to stop leaks, tells the delicate lithography machines to pull back their sensitive parts, shuts down the elevators, secures the power. It's a full-on damage control plan that happens before the first real shake is even felt. And the system isn't just guessing. The trigger logic is unbelievably precise. The sensors are looking for something very, very specific in that first P wave. If they measure a vertical ground movement of just half a centimeter, that's it. The system knows a big one is on its way and triggers the shutdown. It's not just reacting, it's predicting. So when you put this all together, what you've got is, well, it's not really a building. It's more like a living organism designed from the ground up for one single purpose: to achieve perfect, absolute stillness. I mean, just look at this defense-in-depth strategy. It's just a masterclass in engineering. You start with trenches to block traffic. Then you use base isolation to skate through an earthquake. You use a structural break to create a quiet little sanctum inside. You use active control like noise-canceling headphones for the tools. And you top it all off with a sensor network that sees danger before it even arrives. Each layer has a job, and they all work together in this symphony of stillness. And the reason any of this matters, the so what, is that this insane quest for stillness is what makes our entire modern world run. The circuits in the phone in your pocket, the computer you're watching this on right now, every single one of them was born on this perfectly engineered, perfectly still canvas. It's truly an incredible achievement. Which, it leaves us with one final kind of mind-bending question. All of this complexity and genius, this is what it takes to build a 2-nanometer chip. A 2-angstrom chip is 10 times smaller. What kind of physics-defying world are we going to have to build to make that a reality? Thanks for watching.